You might be familiar with sequences and series from GCSE, however at A level they come in a slightly more complex form. They come in three different types. They are recurrence relation, arithmetic, and geometric. We're going to go over each of those in more detail in a little bit, but first we need to go over some of the notation that is now being used. At GCSE you might be familiar with the nth term. That is still used but in a slightly different way, and there are a few other things you need to learn with regards to each of the individual types of sequence and series. First off, there's a difference between a sequence and a series. A sequence is just a list of numbers connected by a rule, for example 1, 2, 3, 4, 5, 6. In a sequence the numbers are written separated by a comma and are simply left as a list. A series is just all of the numbers of a sequence added up together. If the series goes on forever, it can just be left as a list, like so. But if you are told the nth term of the series, then you can just add them all up into a number. Just like at GCSE, each term of a sequence or series can be given a number, referred to as n. The first number in a sequence or series is n equals 1, the second is n equals 2, and so on. The nth term is used to refer to the formula used to find any number in the sequence. So if you wanted to find the 100th number in the sequence, n would be equal to 100, and you simply substitute n into your formula to find your term. In this very simple example, the nth term, shown as un, is equal to n. So the 100th term, you substitute n, and u100, that is the 100th term in the sequence, is equal to 100. With the basics out the way, we can move on to arithmetic sequences. You should be fairly familiar with these from GCSE. It's just a list of numbers that increase by a certain amount each time. In this example, 3, 7, 11, 15, and so on. As you can see, each time the number increases by 4. This common difference is referred to as d. The very first term in any sequence or series is always referred to as a. An arithmetic series is simply all of the terms in a sequence added together, so u1 plus u2 plus u3, and you get the idea. However, you can notice a pattern emerging when you substitute the common difference for d, because it's an algebra you can use it to find out patterns. If the first term is a, the second term is always going to be a plus d, the third term a plus 2d, and so on. You can notice that the coefficient of d is always equal to n minus 1, so the 100th term, u100, is always going to be equal to a plus 99d. Using this you can construct a formula that gives you the nth term of any arithmetic series or sequence. un is always equal to a plus n minus 1 times d. The trouble is that some series can be very long. What if you wanted to add up the first 150 terms of a series, say? Writing out all 150 terms and adding them up together manually would take a very long time, so we can use algebra to solve that problem as well. In general, the sum of a series up to the nth term, Sn, is equal to a plus d plus a plus 2d plus a plus 3d, and so on until you reach a plus n minus 1d. This is the very last term in the series, and that is where it ends. That is your final term that you are adding up. And with that in mind, we're just going to flip it round, so that it reads backwards. Because you can do addition either way, this doesn't make much of a difference numerically, but it does make the next few steps a bit clearer. Now we're just going to add the normal formula and the reversed one together. While this shouldn't make much of a difference apart from doubling it, it does show up an interesting pattern. This makes 2Sn equals 2a plus n minus 1d plus 2a plus n minus 1d plus 2a plus n minus 1d, and so on n amount of times. We can simplify that by saying 2Sn equals n times 2a plus n minus 1d. Then we can just simplify the formula to get Sn equals n over 2 multiplied by 2a plus n minus 1d. That formula, with n, a and d substituted in, will give you the sum of a series up to the nth term. However, we can simplify this a little bit further. We know that the last term, we'll call this L, is equal to a plus n minus 1d. By substituting this in, we get Sn equals n over 2 multiplied by a plus L. If you didn't really understand the proof, it doesn't matter. But what is important is that you remember these formulae, and that you can identify A, the very first term in the series or sequence, N, which is the number of the last term in the series or sequence, and D, which is the common difference between terms. Remember, this only works for arithmetic sequences or series. Moving on, we can have a look at recurrence relation. These are in many ways similar to the other types of sequence or series, but the thing that sets recurrence relation apart is that it uses the previous term in constructing the next one. For example, u k plus 1 is equal to 2 times k plus 2. What this effectively means is that to get the next term in the series, you take the previous one, multiply it by 2, and add 2. Most of the time, recurrence relation questions will give you the first term, u1, to get you started. In this example, u1 is equal to 3, so u2 is equal to 2 times 3 plus 2, which is 8. Therefore u3 is equal to 2 times 8 plus 2, which is 18. u4 would be equal to 2 times 18 plus 2, and so on. Some of the time this will cause the sequence or series to keep on going forever, getting larger and larger. However, a special feature of recurrence relation is that it can converge to a certain number. This is because the difference between each term gets so tiny that it doesn't really make any difference at all. In converging sequences, the sequence will reach a number and then continue being that number forever. We can use this to find out what the convergence point of a sequence is. Because uk and uk plus 1 are so close that they're almost the same, we can just substitute them both for L. At that point, you just have an algebraic formula you need to solve. By rearranging, you can find out what L is equal to, and that will give you the point towards which the sequence is converging. The third and final kind of series or sequence is geometric. This is very similar to arithmetic series and sequences, except this time you multiply by a number instead of adding one. This is called the common ratio, and it replaces the common difference which you find in the arithmetic. In this case, you have the sequence 1, 3, 9, 27, and so on. Each time the number multiplies by 3. This is called the common ratio and is signified by r. It behaves in a very similar way to d in an arithmetic series or sequence. And in the same way, you can make a formula. A is still the first term in the sequence. The second term would be AR, the third term AR squared, the fourth term AR cubed, and so on. Using that pattern, you get UN equals AR to the power n minus 1. However, geometrics are a bit more complicated, because you're multiplying by number. If r is greater than 1, then the number will get bigger, but if it's less than 1, it will get smaller. This means there are two different formulae to get the sum of a series. Modulus is a function that effectively removes the negative part of any negative number. Therefore the modulus of minus 1 is 1, but the modulus of 1 is still 1. It just makes everything positive while retaining its numerical value. You'll need to bear this in mind while we're looking at the formulae. If the modulus of r is greater than 1, then Sn is equal to a times r to the power of n minus 1 all over r minus 1. However, if r is less than 1, then the 1's and the r to the n's switch round. So Sn is equal to a times 1 minus r to the power of n all over 1 minus r. It's important to remember which formula you need to use for which value of r, and always remember to use the modulus. If r is negative, then just make it positive using the modulus function. If you forget either of these things, you will come up with a wrong answer. Geometric series have another special feature, if the modulus of r is less than 1. This is called the sum to infinity. Because the terms will always tend to 0 if the modulus of r is less than 1, i.e. it's a fraction, you can add up every single number in the series up to infinity and come up with a definitive answer. This doesn't work with the other types of series because the terms will never tend to 0, but in a geometric series, there is a simple formula you can use to find the sum to infinity. S infinity is equal to a over 1 minus r, assuming that the modulus of r is less than 1. If the modulus of r is greater than 1, the terms will always be getting bigger, and sum to infinity won't work. Let's look at an example. In a series where r is equal to a third, and a is equal to 3, the sum to infinity is equal to 3 over 2/3, which is equal to 9 over 2. This is the number you will get if you add up every single number in the series. It may seem strange to add up an infinite number of terms and still get a finite answer, but bear in mind that in this series, each term is getting smaller by a factor of 3 each time. This means that a vast amount of the terms will be infinitely close to 0, and if you add up the first few terms with an infinite amount of zeros, you will get a finite answer. That wraps up our guide to sequences and series. If you want more guides, head over to youtube.com/Cosbicmaths.